So as we've done hypothesis testing for quantitative variables using a z-test or t-test or one sample or two sample, there's also hypothesis testing for categorical variables. So for categorical data, we use a chi-squared test. And there's two types of chi-squared tests. Really, the first one is the goodness of fit test, and that's basically where we try to see if what is occurring with a categorical variable is actually what we expect to occur. And we're going to look at that one first. And the second two use the same type of chi-squared tests. It's just how we write our hypothesis or what we're actually looking for is different. So let's go ahead and look at just what a chi-squared test is in general. So in general, we're using categorical variables. The good thing is we make our decisions based off p-values just like we did before, comparing it to an alpha, just like we did with z and t tests. And instead of a z or t, though, we're using a chi-squared test statistic. That's why it's called chi-squared, because it's a chi-squared test statistic that we're actually using to calculate our p-value. And our calculator will give us that. The difference is also in the distribution and how it's shaped. It does have degrees of freedom, just like a t-test or a t-distribution, but the difference is how the degrees of freedom is calculated because we're doing categorical variables. So we're not just taking our sample size minus 1, we are doing something else to find our degrees of freedom, which I'll talk about when we do it. Notice here that as the degrees of freedom increases, the curve actually flattens out and gets more normal shaped. So I think it just makes sense to do a problem. So let's suppose we have this situation where we have a census that tracks in Dallas County, Texas, and takes a random sample of 40 predatory lending businesses with Dallas, Texas addresses, and they mark them on the map. So they want to figure out, do these type of businesses tend to be located primarily in lower income regions, or are they found proportionally in regions of all income levels? So we're trying to see is what is already occurring actually what we expect to occur. So we're comparing what's occurring to what is expected. So we're dealing with categorical variables. If we break income down into different groups. Now this would already be given to you as far as how many businesses were in each income level. And then it also would need to tell you what percentage we would expect to be in each income bracket. So these are the percentages we would expect to be in each income bracket. Now, these are the actual counts of the 40 businesses and how many were in each income bracket. So we're trying to see is what is already occurring lining up with what we expect to occur. All right, so with the hypotheses for a categorical variable, a test for a chi-squared test, we are still doing HO as we did before, saying that they're equal. So basically, what is occurring is what we expect to occur, saying that there's no difference. The HA is saying that, oh, okay, no, they're not equal. Something's different. So that's the difference in HO and HA. But notice, unlike Z and T tests, we don't have to have inequalities here. We don't have inequalities. It's simply saying that they are equal. Basically, what's occurring is what we expect. Or HA, what is occurring is not what we expect. So we actually are going to state these in words. Notice, since we're dealing with categorical variables, we're going to state our hypotheses in words. And there's another way to say it down here. Basically, for this particular problem, we could say the distribution of predatory lending businesses in Dallas, Texas is the same as the proportions of households in the specific income bracket. So remember that saying that they're equal by saying they're the same. The same thing we've been doing for HO the whole time, saying that they're equal. And HA is saying that they're different. Now, we wouldn't necessarily know which category was different, so we would simply say at least one proportion is different. All right, so we know we're doing a chi-square goodness of fit test since we have multiple categories, and we're dealing with one variable here. And we're just trying to see if we're doing one sample and one variable. We're trying to see if it's different from what we expect. So that's how we know we're doing a goodness of fit test. If we're trying to see, does the data from our sample fit good with what we expect to be occurring? Now we do have to check conditions, as we have to for our Z and our T test when we do inference. These are the conditions we need to check. We need to make sure it's from a random sample, or a randomized experiment would be doing the same. And we also need to still check to make sure the sample is less than 10% or equal to 10% of the population. And the last thing is we need to make sure that the expected counts, not what we actually currently counted in our sample, but the expected count should be greater than 5. So this is the new condition you need to check for categorical data when doing a chi-square test. So if we look at this problem, we know it comes from a random sample of 40 predatory lending businesses because it says that in the problem. We can definitely assume that 40 predatory lending businesses is less than or equal to 10% of the total amount of businesses in Dallas, Texas. And to verify what we expect the counts to be, in order to see if they're all greater than 5, we need to take the proportions and actually multiply by the sample size. So if you take the proportion, multiply it by the sample size, we can expect there to be 18. If we take the proportion, multiply it by the sample size for this category, we expect to be 11, and etc. So notice all 3 of these expected counts are greater than 5. Now remember, our goal is to see is what is occurring in our sample basically the same as what we would expect. Now obviously there's a little variation, so our p-value is going to tell us the probability of getting a sample like this if we expect these values. So in our calculator we can run the test. Now what we're going to do is we're going to put our actual values from our table in our L1, and we're going to put our expected counts in L2. So I'm going to go ahead and show that in my calculator, and we're going to go to this test. Once you see here, or if you see here, it's a chi-squared goodness of fit test. And notice we're going to put our degrees of freedom in there, and I'll go ahead and tell you what that is. Down here it says it's the number of categories minus 1. So that's how you find your degrees of freedom. It's not sample size minus 1, it's your number of categories minus 1. So when you're dealing with categorical variables, we're actually dealing with categories. So we have to think about the degrees of freedom having to do something with the number of categories. So that's how you find it when you're doing a goodness of fit. So I'm going to go ahead and pause this and pull up my calculator really quick. Alright, so I went ahead and put in my data in L1 and L2. Remember, I'm using the actual data, so what's observed, and then what we expect based off the proportions in that sample of 40. So now we're going to go to stat, over to tests, just like we would before. I like to go up since the chi-squared tests are closer to the bottom. And notice I'm going to choose chi-squared goodness of fit test. I'm going to hit enter. Now, where our observed values are in L1, expected are in L2, make sure you change degrees of freedom, because degrees of freedom will be default to a number and you definitely want to change it. So your degrees of freedom is the number of categories minus 1. So if I could just go back, notice we have 3 categories. 3 minus 1 is 2. So our degrees of freedom is 2. If you forget to change that, it will give you the wrong answer. So make sure you get the right answer. So if you go to calculate, it'll give you some information here. So it gives us our chi-squared test statistic. It's kind of like your Z or your T from your other tests. It gives us our p-value, so the probability that this sample would occur if our null hypothesis was correct, and our degrees of freedom, which we put as 2. What's down here, these are called contributions. Basically, these numbers down here are in order based off the categories we put in. So, and this is how much each category is contributing to the test statistic. So really, the one with the highest value is the highest contributor, meaning that if we say what is currently occurring is not what we expect, then we could tell which category is making the most difference in that, in changing that. And notice the one category with the highest contributor is the third one. So this category here would be making the most change if we say that there's enough evidence to reject the HO. And so let's go ahead and look at the rest of that to see what we would decide based off of our p-value. Just back over here on the PowerPoint side, I highlighted the p-value here. And once again, I described what those contributors are. This is the formula we would use if we had to calculate the chi-squared test statistic by hand. That is on the formula sheet, but once again, you can use the calculator to find it. So why do it by hand? The second image here is if you chose draw, this is what you would see. So it just gives you that test statistic and the p-value, just like when we did draw for Z and T. So notice our degrees of freedom is really small, so it's not flattening out much. It's not looking bell shape at all. So this is what it looks like here. So now we can go ahead and make a decision. Click that. So notice our p-value is really small. So since our p-value, we use the same alpha concept. So if we have no alpha given, we're using an alpha of 0.05. So our p-value is a less than alpha. So since our p-value of 0.0208 is less than alpha of 0.05, we reject the HO. So since we're rejecting HO, we're saying there is convincing statistical evidence that the distribution of predatory lending business in Dallas, Texas is not the same as the proportion of households in the specific income brackets. And once again, if they ask us a question like, which category do we expect is contributing to this difference the most, well then we would say this one here based off of that contributor, the number here in our contributions being so the highest. Notice here the 5.11. So that is how we do a goodness of fit chi-square test. And I'm trying to see if there's anything else I have here. Okay, so this was just a tip I have. Let's say they gave you, if they give you the chi-squared test statistic, so they give you chi-squared, and they say, what is a p-value that goes with a chi-squared of 7.742 with the degrees of freedom of 2? Well, if they give you some information, not the actual table of data, and they want you to find a p-value, the same way we use normal CDF to find the percent or probability above a certain cutoff or below a certain cutoff, you would do the same thing here. So these are screenshots, but I'm going to do it, run it really quick. So we would go to the same way we'd find normal distribution, our inverse norm, our normal CDF, and inverse norm. You do second bars, and we are going to do a chi-squared CDF instead of normal CDF. Let's say they gave you a test statistic of our same test statistic of 7.746. That's going to be your lower bound. Your upper bound, we use positive infinity. I was going to say negative, but we're doing it. Notice where it's always right-tailed for a chi-squared test, so we always use positive infinity as the upper bound. They used 1,000 because really a big number is a big number when you're dealing with this, but I'm just going to continue to use our positive infinity like we have been doing. Degrees of freedom, we know is categories minus 1. Number of categories minus 1. Paste. And hit enter. So there are only 3 values: lower bound, upper bound, and degrees of freedom. And once you hit enter, it'll give us our p-value. So I would only use this if they didn't give you the data. If they give you the data in the table, then just put it in the calculator and get everything at once. No sense in wasting time. All right, so that is the goodness of fit test. If you find this simple, then feel free to continue watching to do the other 2 type of chi-squared tests. This is one example. You can pause it here. Try this one really quick just to see if you can figure it out. If you paused and I unpaused, there's a tip. Because you're probably wondering, well, what percent would I expect? Well, there are 4 quadrants. The expected proportions are that each proportion is equal to 0.25, since there are 4 quadrants equally spaced. And I'm just going to click through the answers here